We're now in the era of the satellite mega constellation. There are thousands and thousands of satellites today, thousands more being launched all the time. And through the various constellations, it's anticipated that we could see as many as 100,000 satellites in orbit around the Earth in the early 2030s. That is a lot. Like when I started, there were maybe 2,000 satellites. So 100,000 is a lot of satellites. And they add light pollution. Even if you do the best you can to try and minimize and mitigate the amount of light pollution, there is both the direct light pollution that you get as these satellites are passing through the field of view from your telescope, as well as just an overall increase in sky glow that's coming from all of these satellites all at the same time. And so the hunt is on for ways to try and mitigate this. And I'm sure you've heard all the various ideas, like let's make them lower profile. Let's try to angle the solar panels away so that they don't glint off the sun. And then an idea that I hear all the time is, why don't we paint them Vantablack? This is a coating that absorbs almost all of the light that falls on it. Things that are painted this color are just almost impossible to describe how dark and black these objects become. And so this is an idea that has been thrown around. And in fact, my guest today is in the process of doing this. Dr. Noelia Noël is a senior lecturer at the University of Surrey, and she is working on a new CubeSat satellite and has been worried about the light pollution that's going to come from the satellite and has been researching ways to be able to darken it and came across the same idea of painting it Vantablack 310. She has done some tests in the lab with this material and seen some really promising results. And so in this interview, we talk about the size of the challenge, what astronomers are experiencing as they're seeing more and more of the sky glow, as well as direct paths through the objects that they're trying to image, as well as the mitigation strategies. And we focus on what are the results so far that she's seeing with Vantablack and what we could hope to see as an overall darkening of satellites and try to mitigate this problem of satellite light pollution. All right, enjoy this interview with Dr. Noelia Noël. Noelia, can you give us a sense of the scale of the light pollution that astronomers are starting to see from satellite mega constellations?
Yeah, thank you, Fraser. This is a very worrying problem for astronomers. We are at the point in which 30% of the astronomical observations have to be discarded because of the pollution from mega constellations, satellites, and so on.
And just to be clear, like I've done my share of astrophotography in the past, and you will like take a bunch of frames and then you'll get a satellite trail passing through your image. And you're like, well, that one's out. And then you've got all the data that remain. Is that the same situation, or is it the problem is that they're actually going right through the kinds of objects that the astronomers are looking to observe?
Yes, that's the main problem. And also, when we do amateur photography, it's our time and our own resources that we are wasting. But in this case, is the taxpayer money. These telescopes, each observing night at these telescopes is like $10,000 to $50,000 per night. So it's a lot of money that we are wasting. So it's a huge problem.
Right. So in my case, I just have to take another 10 frames to get the image that I was hoping for. But in this case, each astronomer is allocated a certain amount of time, and then the telescope has to move on to the next person. So it's this degradation of their overall imaging. And you give me this 30% number, but we're really at the dawn of the age of the mega constellation right now. How bad is this problem expected to get?
Well, that's a very interesting question, and I don't think I have the answer for that. By 2030, we believe that there will be around 100,000 satellites, but the actual specific number is really, really difficult because all of the big companies, they don't disclose this information. So if we don't do something right now, the problem will be way worse.
Mm-hmm. And what kinds of observatories are most vulnerable to satellite trails?
Well, actually, we're living in a very extraordinary time for astrophysics. There are instruments like the dark energy spectroscopic instrument, the DESI survey, the Vera Rubin Observatory that just saw its first light a month ago, the James Webb Space Telescope, and these are transforming our ability to study the universe, from the formation of galaxies to the life cycle of stars, planet formation, and these important tools hold the key to understand the fossil records of our universe are at high risk with these satellites.
But I know that, for example, here we can see the satellites in the early evening and in the dawn before the sun comes up, and that's just because the sunlight is hitting the satellite before it's hitting, the mountains around me. And so, are there certain kinds of surveys that are more at risk to, this kind of satellite pollution?
Well, yeah. So at the minute, we are seeing for example, with the CAM, the dark energy camera, we are seeing that the surveys that require to study objects at higher redshift, they are very damaged, because you need to have a very very detailed observation, backwards in time. And so removing a little piece of the information from these images is a huge loss. It is a paradox, because these tools are becoming more powerful, if you want. So the environment we observe from is becoming more polluted. So although we have this new technology, but this is more polluted because of the rapid development of these satellite mega constellations, the Starlink or the OneWeb, and these objects have introduced this new kind of pollution that is the light pollution. We always had pollution problems for ground-based observatories from the lightings, but now we have this new added problem. And for observatories like the Vera Rubin Observatory, the risk is very severe, with satellite streaks ruining, as I said, as much as 30% of the exposures.
And it's not just the actual streaks themselves. I understand that the satellites just contribute to an overall general sky glow that is making the observations more difficult.
Yeah, that is actually true. So that's why the IAU, so this is the International Astronomical Union, they have a threshold that they recommend to minimize the interference with the professional astronomical surveys. And now we are at risk of exceeding that threshold.
And sort of, I reached out to you because there was an article that you did about on the conversation about sort of the scale of this, and talking about Vantablack, which my audience is really excited to find out how well Vantablack works. But I want to talk about those levels, because you identified in your article that there are certain magnitude levels that the IAU has identified as ideally to try and keep the satellites below this level of brightness. How well have the satellite providers responded to the astronomical community to sort of help deal with their concerns?
Well, that is a very interesting question, but not one that I have the answer to. To begin with, I'm not an expert on Vantablack, but when I started reaching out to my colleagues who work on nanomaterials a while back, they were telling me that the main problem is that you cannot spray the painting. And now that has changed. There is the new technology like the Vantablack 310 that you can directly spray. So SpaceX, they have commented on our research, not directly to me, but to the BBC, for example, saying that they tried some mitigation strategies with an ultra black coating, but they had thermal issues.
Yes.
But I haven't heard any of the specifics. We are hoping that with this new technology that my colleagues are developing, and the incentive to develop is because there's no, actually almost no funding for this. It's just me emailing them and telling them, oh, please, can we try this on satellites? Are you developing this? And they were like, yeah, well, but we do this more for Formula One, and I don't know. Oh, please. And then they got really excited because I said, we have actually a satellite that you can try it on, and we can test it within our labs, and we can launch this satellite, so it can be something really exciting. And they got really excited, and so the thing is that at the minute, it seems to be passing most of our lab tests really well. It's not overheating, and we are hoping to actually test it in orbit in 2026. So far, it's going through all the tests and is giving us really good results. But as I said, we haven't tried yet on a low Earth orbit satellite.
So give me a sense. I've never experienced Vantablack. And I know that there are like various, you can go to science shows and exhibits, and that you can actually go into rooms where they've painted it. And so now I'm assuming you've had a chance to interact with this stuff. What's it like to hold something that is painted with this light absorbing material?
It's absolutely amazing. So I never imagined that there are so many shades of black. I mean, because you always think that black is black. Well, actually, one thing that I learned is that the first thing I learned is that Vantablack is like a legacy name when it was grown as a forest of vertically aligned carbon nanomaterials. That's what I was explaining before, that my colleagues were saying, no, this is, and that was for defense application. And I saw these early Vantablack samples. And then when you compare to the new Vantablack, you say, oh, that's not black, that's gray. My colleagues, when I went to the company, to Surrey Nanosystems, for the first time, they showed me a picture. And it was a black picture, right, like this. And they say, yeah, this is a 3D picture, but it was just like something really boring, like, don't know, like looking at my phone screen like that, all black. And it was like, and so when I move around, it was actually a face, like a 3D face. So you see actually like a 2D black thingy, and it's a face. So this is how amazing this new paint, Vantablack 310 is. It's very black, and it's reflecting only about 1% of the incident light when you put like a laser on it, while the other ones you can see more reflection with the previous version. So with this, we're hoping that it's dark enough to reduce the satellite brightness to below the magnitude that the International Astronomical Union recommends.
And so give me a sense of that. What is the official recommendation by the IAU, and what kind of a decrease in magnitude do you think you're seeing with something that would be painted Vantablack?
Well,
I guess it depends on the size of the object and so on, but...
Yeah, so what the IAU recommends is 7 in the AB magnitude system. So just to give an idea, so this is a logarithmic scale. So each step of 1 magnitude means a factor of 2.5 times fainter. So an object at 7 AB magnitude is just below the threshold of naked eye visibility under very dark skies. So most people can only see up to a magnitude of 6 with a naked eye. So this 7 AB magnitude will be faint enough that it won't significantly interfere with the sensitive telescope like the Vera Rubin Observatory that I mentioned before. So you will be able to get this, to reduce the satellite brightness to 7 AB magnitude. So you will dim it enough that it will blend into the natural sky background and doesn't contaminate the astronomical images.
Right. But I mean, a 7th magnitude object is easy to see in a pair of binoculars, in a small telescope. As soon as you take a long exposure picture, I'm sure it passes. It's quite obvious. So didn't they set even more stringent guidelines? Wasn't that their preference, to get even fainter than that?
So I was just explaining what an object at 7 AB magnitude will be. Ideally, it would be better to go even deeper.
And so if you take a thing that is 7th magnitude and you paint it with this Vantablack, how much of a decrease in magnitude do you think, does it seem like you're going to be able to get?
We are hoping that, for example, in rural skies, when you have a very, very dark sky, it will be just below that naked eye visibility. What reducing to magnitude 7, will be, and why we're using this as a reference is because current satellites without mitigation can be as bright as magnitude 1 or 2, for example. That is a dozen of times brighter than magnitude 7 because of the way the scale works. So, for example, if we think about the brightness of Starlink V1, the AB magnitude will be around 1 or 2, and this is extremely bright.
Yeah, it's very bright.
And then if we coat this will get to magnitude 7, and this is much brighter, less disruptive, and so reducing the satellite to a 7 AB magnitude will mean that it's 100 times to 1,000 times perhaps fainter than the uncoated satellite. So it will be something like that. So it seems to be a very small number, but is faint enough to avoid triggering algorithms that you need to use to reduce your data to minimize the brightness, for example, with LSST or with the CAM.
I see. So like where I live in Bortle 3 skies. So they're very dark, Bortle 2 to 3 skies. So I live in a place I can see the Milky Way and I can see plenty of satellites, but I can't see any Starlinks. But you can see the Starlinks when they're being deployed and then they eventually get too dim and then you can't see them. I mean, if we could see all the Starlinks, the sky would look bizarre with all of these little dots of light, but we don't see them. So they're definitely below visual magnitude right now. But it sounds like there's this limit where if you get one of these star trails and it's not very bright, in your image, then it doesn't impact your data very much, as opposed to one that is, oversaturating tons and tons of the pixels as it's moving through your field of view. I mean, it's mitigation, not removal.
It's mitigation, yeah. I mean, as I say, we don't know the amount of objects that we are going to have, the amount of satellites that we're going to have in the next 5 years. So in the past 5 years, companies who launch, or countries who launch satellites, launch more satellites in the whole history since we started the space exploration. So this is a huge problem. I don't want to say that they are being non-transparent, but they are not disclosing the amount of satellites that they are planning. Perhaps they don't know, but what we know is that probably will multiply or even triplicate by 2030 in 5 years. So imagine that we have a Rembrandt, a beautiful Rembrandt, and then we scribble all over it, or we go to the Louvre in Paris, and then we just decide to highlight the Gioconda, the Mona Lisa, and that is what we do into the astronomical images. Not only for me as a professional astrophysicist, these are actually a piece of art, because it's not only science, it's the legacy that we have from from our place in the universe, and we are ruining it.
Now, an argument that I hear all the time, and I have my answers for dismissing it, which is that why, astronomers should just use space telescopes instead. How do you must get this all the time too. How do you respond to that?
Well, it's very expensive to have a space telescopes. It's not a cheap solution. I mean, we know what happened with James Webb. It's been in the pipeline for 3 decades or more, and it now launch, but it's not something that we can say, let's launch. Financially, it doesn't make sense. Also, with a wide field camera from a ground-based telescope, you can have a very, very wide field of view. For example, the field of view of the Hubble Space Telescope is like a little dot compared to the wide field imager in the DECAM in Chile, for example. So you have like the difference will be this compared to a microscopic dot that you cannot see. So this is a very important, and also because you live in rural Canada. I come originally from Argentina in the south, that is quite rural and quite dark. But here, where I am in the UK, we've seen that these satellites are more and more affecting the observation, and that's something not allowing people to have the equal opportunities that we had as children. Skies should be a social justice matter. It shouldn't be only for a privileged ones. And so we already have the problem of people living in light polluted cities and who don't have access to the night sky. But now, even people who originally will have access to the night sky will have this pollution from satellites. So I will say that, space telescopes are lovely, but it's not the point.
Yeah, I mean, I think I look at the costs. For example, even Vera Rubin, which is the most exciting telescope around, it's in the $1 billion range. The upcoming extremely large telescope, the largest telescope humanity's ever built, it's like 1.2 billion euros. That these things are still a fraction of the price of space telescopes, and yet, if there's a problem with the ground telescope, you can swap out the instruments. You can, as new techniques are developed, new cameras are built, you just can, you upgrade them and just keep going. That you don't have to worry about them running out of propellant out there in the middle of space. There's so many good reasons. And then the other thing that I think you mentioned there is that it's not just satellites, it's just light pollution. That if people are angry about light pollution from satellites, they should be angry about light pollution in cities. That people are pointing their lights diagonally and up, and they should be pointing them down, please. So I want to talk about your specific satellite that you're working on. So is this an actual, like, it's a CubeSat, and does it have a purpose, and you wanted to see what would happen if you painted it Vantablack, or is it purely just a test for painting something black?
Well, actually, we are planning this code. As I said at the beginning, I got really excited about trying to find a way to paint satellites. And this all started a couple of years ago that someone from NASA came to my institution and they were mentioning this and that about satellites. And I was like, oh, are you doing something to mitigate light pollution? Are you painting something? And they said, no, that's, no. So they completely minimized the issue. So, I didn't. So I started thinking, oh, no, what's going on? And so when I found out that in the Surrey Space Center, the space center from the institution where I work, they were working on a CubeSat called Jovian 1. And Jovian, it has nothing to do with the planet, with Jupiter, but it's the Jupiter collaboration between three institutions, between Portsmouth, Southampton, and Surrey. So I wasn't involved in this. I'm an astrophysicist. These were space engineers. But when I found out about this CubeSat, I thought, oh, okay, so I will go and take a look at the Space Center. And my office happened to be there now. So I was moving office. So I was like, with the excuse of looking into my new office, I was like going down to the labs and talking to the engineers. And then I said, oh, so for example, if I will be able to contact people who can do a little bit of a spray in one part of your satellite, will that be a possibility? And they were like, oh, yeah, sure, of course. This is the main goal of the Jovian 1 CubeSat is, this partnership, but is for training students. And that's something I'm very passionate about, trying to create and spread the knowledge of science and space among the young generation. So yeah, they said, oh, okay. And actually, I thought, when you think about a CubeSat, you think about this, it's like a tissue box, like a square tissue box. But this one is quite interesting. It's like a cereal box. And it has like the solar panels are like 1 meter long. So actually, it's actually a quite substantial apparatus. So I thought, oh, okay, so maybe we can paint a little bit of this. And they said, yeah, maybe we can do the back of the solar panel. And I was like, wow, jackpot. And so I contacted my colleagues in Surrey Nanosystems, and they said, yeah, so we can try. So they started developing this Vantablack 310 a little bit further. And then, we started doing the first test. So it's all like coming together. As you probably know, we don't know if the mission will succeed because, there's always a 50-50 chance. But if it does, it will be really amazing from the point of view not only of the light pollution mitigation, but also because it's a collaboration between these three institutions with the students involved.
And so you've painted the backs of the solar panels and you've painted the body of the CubeSat at this point?
We haven't done that. So they are still developing the CubeSat. We did some testing with some prototypes.
Okay, I see.
Yeah, but the idea is to be able to paint the back of the solar panel.
Right. And that's as you say, if they stretch out 1 meter on either side, that's a pretty large surface area that you're going to have to mitigate. And the tests that you've done, I mean, the issue that I hear is heat is the main challenge in this. And so with the experiments that you've been doing, how does it change the heat profile of the spacecraft?
Well, actually, we've been doing this test in the lab. Is actually much better because the problem with a black surface obviously is that it will absorb more solar radiation, right? And so the solar panels are actually thermally quite sensitive. So this can raise the internal temperatures beyond safe limits. But we actually have been testing, and my PhD student has doing this work, and it actually is not affecting as much as it was originally thought, and actually much less than what is it's disclosed by these companies. I don't have the specific percent.
That's okay.
Yeah,
it's okay. Yeah, but I'm sort of envisioning that, because if the solar panels are facing the sun, then the parts that are painted black are facing away from the sun. They're in the shade of the satellite, and so then you're getting advantage of black being a better radiator. And so there must be some kind of balance here that's going on that you're doing. But obviously, many, many more tests. How has been the response? I read the paper on the conversation. Are you finding that other researchers who are working on their own CubeSats or even larger satellites are reaching out to you and asking for your experiences?
Well, I had it has been super positive because this is a win-win situation for everyone. If you think about this, it will make a satellite much more sustainable. And so from the satellite companies from their side is actually a win-win situation, and also from astronomers, because astronomers are really worried whether astrophotographers or professional astrophysicists, everyone is really worried. So everyone has been very positive. They're all waiting to see whether this test will provide the result that we're expecting. But as I said, we validated. We did testing in thermal vacuum chambers and things like that, and everything is looking really good at the beginning. So there's a lot of hope for this new paint. As I said, we are working together with the space engineers, so it's not like we're doing this from an astronomical point of view only. So I think it will bring the communities together, unlike other aspects of satellites that might be a little bit more contentious. I think this is a solution that will benefit everyone, obviously if this is not causing this thermal heating.
And so if all goes well, when will you see the reality? When will your spacecraft hopefully launch?
Well, we are hoping early 2026. So again, so this is not something that is dependent on us. It's mainly, when this is going to be a launch from the UK, so we need to, secure the launcher, prepare everything for the launch up in the Shetlands, and then do the launch, and then hoping that this will be successful. So it's a lot of things that we need to take into account. And as I say, you might not think that a little cereal box is causing so much so much expectation, but it is the situation. So so hopefully this will be launched in early 2026.
Yeah, engineers who are building satellites are very conservative by nature. And so everyone's going to watch you to see whether or not the experiment works. And then if it does work, then you'll have plenty of people following in your footsteps. But until then, I think everyone's just going to wait and watch and see what happens, because it is so, like I said, they tend to reduce the risks wherever they can. Noelia, what are you obsessed with right now?
Obsessed in terms of astronomy, or
well, so I forgot. Anton, my editor will cut this out, but I forgot to warn you. So the question that I generally end my interviews with is to ask you what you're obsessed with, and the gist of that is just I want to know what you're thinking about, like what kind of ideas, not what you've just gone through necessarily, but what ideas you're really fascinated with. And generally astronomy is what it is. But if it's if you've been watching, if you're playing a video game that you really like, then that's fine too. But yeah, what are your your shower thoughts and things you're like as you're sort of imagining the rollout of various trends in astronomy, new telescopes, technology, that kind of thing.
Yeah, so I'm actually pretty much obsessed with making astronomy more sustainable by, trying to see this through the light pollution mitigation through. But also, I'm quite obsessed with understanding dark matter, that is the scaffolding of our galaxy. For galaxy formation and evolution. And this is something that is my line of research. So I'm really obsessed. I'm really hoping that we are disentangling this further. And hopefully with these new telescopes, and we will manage to finally realize what dark matter is.
Is there... Like when I think about Vera Rubin and Euclid and the DESI survey and the upcoming Nancy Grace Roman, is there one survey, one experiment that you're like really, you can't wait to see the result from it?
Well, actually, there's so many, so I'm not putting all my eggs on one of them, so I cannot really tell you one of them. But Vera Rubin is, I think, is going to be a game changer for real, for our understanding of dark matter. It will map billions of stars and galaxies with an incredible detail of a 10-year survey. So for me, I study stellar populations, as I said before. So how stars within a galaxy behave, to understand how galaxies form and evolve. And for me, so as a stellar populations person, Rubin will let us trace the motions of and distributions of stars in such a detail that it will be absolutely amazing, and then it will hopefully will allow me to understand, as I said the other day, I was saying it will allow me to understand this like the breadcrumbs left behind the interaction with dark matter. So hopefully that will be something that I will be able to see in my lifetime.
Yeah. It's such a funny mystery that is, we've known about this problem for so long, and yet it's been so difficult to tease out any information. And we're at the point now, I always joke about this, that we can use dark matter as a telescope. We don't know what it is, but we can use it as a telescope lens to observe out to the beginning of time.
Yeah.
And it's taken sort of this amount of energy and effort to bring all of these tools finally to bear. And it feels like the right tools have finally shown up to help solve this problem, or at least make serious progress, or at least figure out what it isn't. Yeah. That's where we are right now.
Exactly. So what's exciting about, for example, the Vera Rubin is that we finally will have the statistical power to detect these subtle distortions caused by dark matter substructures. So we will be able to test all these different theories, and it's like switching from a stretchy pencil drawing to a high resolution lapse map of the universe, almost.
Yeah, it's a fascinating time. I always call it the golden age of astronomy, as long as the light pollution doesn't get so bad.
Exactly.
Yeah. No, thank you so much for taking the time to chat, and good luck with your satellite. And I know a lot of people are going to be watching to see whether or not this works, and we could see a lot more satellites follow the same technique. Good luck.
Thank you. Thank you, Fraser.
I hope you enjoyed this conversation with Dr. Noël. I'm going to give you some final thoughts, but first, I'd like to thank our patrons. Thanks to Abe Kingston, Barely Roofing, Brian Bodie, Caradwin, Chuck Hawkins, Commander Balick, Cy Nielsen, David Gilton, and David Matz, Dustin Cable, Evan Pro, Greg Feely, Hudson Moore, James Clark, Jeremy Mattern, Jim Burke, Jordan Young, Marcel Smits, Michael Purcell, Modzo, Paul Roebuck, Ryan Kaidu, Robeck, Sean Sargent, Stephen Fowler Munley, Vlad Chiplin, and Wolfgang Klotz, who support us at the Master of the Universe level, and all our patrons. All your support means the universe to us. So the satellite light pollution problem is already having a pretty serious impact on astronomy. And while we are in the 10,000-ish satellite range, I forget what the exact number is today, getting to the 100,000 when all of these various mega constellations, not just from the US, but think about the Chinese and other countries, it's going to be a pretty populated place. And ideally, these conversations would have been had before these mega constellations launched. There's a lot of things about getting the best way to mitigate the light pollution, working out better ephemeris so that the telescopes know when satellites are going to pass through their field of view and to try to minimize the impact on that. This conversation could have happened and it didn't happen. And so now you've got satellite companies that are in competition. The demand is heating up and they're trying to launch their satellites as quickly as they can. And then in the same time, you've got astronomers that are trying to preserve as much of the sky as they can to be able to continue to do their research. And as you heard in the conversation, saying like just use space telescopes is not a very useful recommendation. Space telescopes are expensive. They're short-lived. That there are a lot of challenges to be able to develop a space telescope, and that for the cost of one large space telescope for several $billion, you can build networks of ground-based telescopes. So there is a place for both, and hopefully we'll have some kind of future where both can live together in harmony. But it's getting harder and harder for that to happen. I'm not sure how this is going to play out into the future, but I don't think it's going to be great. All right, we'll see you next time.